So in the previous lecture, we talked about the definitions of optimization. What are the main components of an optimization problem? We talked about objective function, variables, and constraints. Now we are going to talk about the mathematical formulation. We want to consider three different scenarios and see in which scenario optimization makes sense. So, scenario 1. In the first scenario, number of variables is equal to number of equations. Number of equations. What I'm going to do, I'm going to show the number of variables by n and number of equations by n. This is the notation that we are going to use in this lecture. So in the first scenario, m is equal to n. In this case, the problem is basically an algebraic problem. And usually, it has one solution. Algebraic problem, usually with one solution. All right. So let's take a look at some examples for the case where m is equal to n. So example 1. In the first example, we have two equations and two variables. When we talk about variables, we are talking about unknown variables. Unknown variables. Our example is 2x plus y is equal to 1 and minus x minus 3y is equal to 2. In this case, our problem only has one question. The reason is these two equations are not linearly dependent. What does that mean? That means neither of these equations can be determined by multiplying another one by a specific factor, by a constant factor. Let's try to draw this. All right. The first one is 2x plus y is equal to 1. So this is y, this is x. If I choose x to be 0 in this one, y is going to be equal to 1, so 1 point. If I choose y to be 0, x is equal to be 0.5. This is 1, this is 0.5. So this is one of the lines. The second one, if x is equal to 0, y is going to be minus 2 over 3. So minus 2 over 3. And if y is equal to 0, x is going to be minus 2. So this is the second line. So the answer to this set of equations graphically is the intersection of these two lines. So x0, y0 is the answer to this set of equations. So the reason that we have a unique answer is these two equations are not linearly dependent. Now let's take a look at another example where the two equations, we are still in scenario 1, where the two equations are linearly dependent. So two linearly dependent equations, two unknown variables. All right, so x minus y is equal to 1 minus 2x plus 2y is equal to minus 2. All right. So if you look at this more carefully, if you multiply the first equation by -2, both sides of it, it's going to give us the second one. So x multiplied by -2, -2, -1 multiplied by -2, +2, and 1 multiplied by -2, -2. Let's try to graphically show these two equations. The first one, if x is 0, y is going to be -1. If y is 0, x is going to be 1. So this is our first equation. For the second one, if x is equal to 0, y is going to be again -1. And if y is equal to 0, x is going to be 1. So as you can see, both of the lines are basically the same, which means you have infinite number of answers for this set of linear equations. Now let's talk about the second scenario. In this scenario, m is greater than n, which means the problem is overdetermined. All right, so m was number of equations and n was number of variables. Let's take a look at an example for this scenario where we have two equations and one unknown variable. In this scenario, like 2x is equal to 1 and x squared is equal to 4. So what will happen here? The first equation tells me x is equal to 1 over 2. The second equation tells me x is either plus or minus 2. So as you can see, there is not a unique value for your variable, or this set of equations does not have an answer. The third scenario where we are very interested in is scenario 3. It's when number of equations is less than number of equations is less than number of variables. All right. In this case, we say the problem is under constraint. And what does that mean? It means more than one solution exists. So actually optimization only happens in the last scenario. So only in scenario 3 and actual optimization can take place. What's the reason? Because if we have scenario 1 where m is equal to n, we either have one solution or we have no solutions, or we have unlimited solutions. Oops, my mistake. So we either have unlimited solutions or one solution. In the second scenario, the problem is overdetermined. So usually we cannot solve it. What was that scenario? Where m is greater than n, overdetermined. There is only one scenario where optimization can play a role, and that's where we have less number of equations than our variables. For example, 2x plus 3y minus z is equal to 4, x minus y plus 10z is equal to minus 1. In this case, as you can see, you have 3 variables, but you have 2 equations. So there is not a unique answer. Probably your answer is going to be a space. It's going to be a set of answers, and then using optimization, you are going to determine which one is the best answer given your optimization problem. So let's take a look at an example for this scenario. One equation, 2 unknown variables. Example 1, x squared plus y squared is equal to 4. If you want to show this graphically, x, y, x0, y2. So this is going to be a circle with radius equal to 2. So this is 2, 2, minus 2, minus 2. All right, so as you can see, each of the points on this circle can be an answer to your problem. Example 2, 2x plus y is equal to 3. So if you want to draw this, it's x, y, x0, y is equal to 3, y0, x is equal to 1.5. You just need to connect this line. So every point on this line is an answer to this equation. So what do we do in optimization problem? We determine which of these points is the most optimal one given the optimization settings, given the objective function and constraints. All right. Now that we have an idea of when an optimization problem can be solved, let's look at the problem from a more mathematical way. So what we discussed was components of an optimization problem, objective function, variables, and constraints. So what's our goal? To find the value of variables that either maximize or minimize the objective function while satisfying our constraints. So you can see all major components of the problem: variables, maximize or minimize, objective function, and constraints. These are the 4 important components. So in order for an optimization problem to have a feasible solution, number of variables should be greater than number of equality constraints. Okay, where does this one come from? This comes from the previous discussion that we had, scenario number 3. So only in scenario number 3, you can say that there is a feasible solution for your problem, because you need to have more variables than the number of equality constraints. If for any reason number of equality constraints is more than number of variables, we are in scenario number 2, where your problem is overdetermined. If for any reason, the number of variables is equal to number of equality constraints, then we have scenario 1. In this case, optimization problem is solved. You only need to find the accurate answer for the set of equations, the set of equality constraints that you are given. So usually we show set of variables with a symbol. For example, here, I'm going to show set of variables by x. So x can be a vector, which means x includes x1, x2, and xn. So here we have n variables. And then we have our objective function. Your objective function basically is a function of all variables. For example, it can be a x1 plus b x2 plus h x n, and so on. Then you have constraints. Constraints are usually in two major categories: equality constraints and inequality constraints. So we show equality constraints as g of x is equal to 0, which can be a set of equations that could be g1x is equal to 0, g2x is equal to 0, and so on. And for inequality constraints, we have h of x is less than or equal to 0. It also could be less than 0 in some cases. Again, this is a set of equations. So it can be h1 of x less than or equal to 0, h2 of x less than or equal to 0, and so on. We are going to solve some examples in the next video.